Okay, I like to talk about the Mm1 Queue. That's basically the simplest queuing system. Um, so this MM1 thing, basically, each of these character here represent some property of the system, and refer to the arrival statistics that actually refer to the fact that the arrival statistics is Poisson, and the second M refer to the departure statistic that is actually the departure rate or the service time will be exponentially distributed. But when the departure time is exponentially distributed, essentially it's the same thing as like when there's a packet in the system, the departure is basically Poisson distributed, but since that the departure time, the surface time is exponentially distributed, is more precise. But sometimes I would just say it's Poisson also, even though it's a little bit not exact. And the last one is just saying that there would be like one server in the system. One server. So it's essentially the simplest queuing system one can think of. And sometimes there's a fourth letter here. If there's nothing there, it's basically saying that the queue is essentially have infinite length. So here I don't have it. It means that I can have the queue as long as whatever it wants to be. So to kind of explain this system, we'll use the same picture that we explained the Poisson process. That basically we can think of a time axis. This is just a time axis and partition into a tiny slot. Each of the slot is, or the interval, have a width delta. Now, what we are going to do is just ask like, what's the probability that within this tiny slot interval here, there will be an arrival, and we typically will use this notation lambda to refer to the arrival rate. And mu is basically departure rate. And then in this case, we can just write a state diagram for this system. With the state is basically a variable, or like you can think of just a parameter that will specify the current situation of the system, and will capture all the statistics for the system at the moment. So a very reasonable state will be just the number of packet in the system. If you think of this as basically a server is trying to process some packets, a server node trying to surface some packet, or we can also think of like the state is the number of customers if this is a bank or a department store or like a convenience store. So let's say just think of like its number of packet. Then let's say I can have, originally the system have no packet in the system, then I would just use a state like 0 here to represent that. And in the next time interval, there's a chance that within the first interval that like there's a packet arrive into the system, and that probability, as we discussed last time, will be just the probability is equal to lambda delta if the arrival process is Poisson. And similarly, if the system is originally have one packet in the system, we can have the probability that have like lambda delta to go to have like one more packet in the systems, so that we can go to the state 2. And similarly, if originally in the state 2, there's probability the lambda delta to go to state 3 and so on. So therefore, we have transition probability like this. Now going backward, if originally the system have no packets in the system, there's no way that it can have any departure. So with probability 1, that it will basically stay there. And but if originally the system have one packet in the system, there's a probability mu delta that within that tiny period there's a transition there, that the packet have been served and leave the system. Therefore, like after the delta time interval, that there may be now no packet in the system now. Similarly, if originally have 2 packets in the system, after the interval, there's a chance that with probability mu delta that a packet left the system, and so on and so forth. So this is basically our transition diagram, or I mean the state diagram. And know that like that's a very small chance that to have 2 packets leave the system. Actually, we can think of like the probability is so small because the probability to have 2 packets in the system will be leaving the system will have an order of delta square. Kind of the probability will be proportional to delta square. If we assume delta is very small, then this probability can be ignored. So therefore, we have the no transition that go step like either increase more than 1 unit or like decrease more than 1 unit. Okay, with this state diagram in place, actually we are kind of like 70% kind of finish our analysis in modeling in analyzing the system. So what we are going to do is we are interested to see that if we allow the system to just continue to evolve until a stationary state. Stationary in the sense that the probability will converge to some stationary probabilities. One way to interpret that, like we can imagine that in the morning that we have, let's say we have some parallel universe, and maybe you have like 1,000 parallel universes. In the morning, we have all these 1,000 universes, like just open the store, or like think of it as a store now this time. Open the store, store just open, and there's no customer in the system. Now, as time continue to evolve, these universes will have some of them, each interval, there may be like a customer coming in, a customer leaving the store, and some universe there's no customer going in and out. And so therefore, like if we look at in the middle of the day, each universe can have like different number of customers in the store. And if we want to find the probability, basically if we randomly pick a universe, we want to know what's the probability there's a customer there, or how many customers are there. And this probability eventually will converge in the middle of the day, in the sense that like at the beginning of the day, we'll have the probability that like will have a probability 1 that there's no one in the store, and this probability have no one in the store. Okay, let's say the probability is P0. That's probability that number of people in the store or customer in the store at the beginning time. Let's say the time is 0. it's basically it's just 1. There's no 1 in the store, but this probability will continue to decrease basically, but it will eventually kind of stabilize in the middle of day, and it will be essentially it will be the same for all these probabilities. Like this is a probability of low 1 in the store, let's say for some particular time. This will be the same as like the probability after some delta period of time, let's say some t pi here. And also like we can have, this is like for t pi, this is t, this t plus t pi, let's say. And we also have other probabilities that p1t will be equal to p1t plus t pi, let's say. And this probability at this time here, we will consider these are the stationary probabilities that it's not going to change anymore. So anyway, now what we are interested in is basically to find this stationary probability. We're not interested in like at the beginning that the system is not stationary yet, but at the state that the system is kind of stationary. Now, but be careful that this kind of stationary is kind of different from some other system when we talk about stationary. The stationary here is like the probabilities are stationary. So, but remember that at each time instance, we can only see one universe. So we can think of like we don't know what's going on at the moment. We don't see what the system is like, and we just want to kind of give an estimate that if we don't know what the system is like, then what will be the departure time? I mean the time span for a customer in the system, given that we don't actually know how many people in the system. If we already don't know that there's, like, say, 2 customers in the system, then know that, like, our analysis following this will not be kind of like precisely describing what's going on in the system. Actually, if you think of this, it's kind of interesting. It's kind of similar to quantum mechanics in the sense that, like, okay, I guess I shouldn't go into that because I don't think many people are interested in quantum mechanics, but anyway. So, okay, let's just go into the simple stuff. So maybe you can forget about what I'm talking about here. That's only a little bit I guess a digression of like usual engineering stuff. What engineer is interested in will be just to find the stationary probabilities. So let's do that. And stationary probabilities will be, you can think of like, it's like the probabilities that falling out. You just think of that, like probabilities will become stationary. For example, like for this node, when that's the amount of probabilities you can think of like water flowing going out of this state will be the same as what's going into this state. So therefore, like what's going out of this state will be lambda delta times P0, and what's going into this state will be like P1 times mu delta. So if these probabilities are stationary, then this will be equal, and if this is equal, I can just cancel the delta here, so I will guess P1 is just equal to lambda over mu P0, and this lambda over mu I can denote rho as lambda over mu, so therefore I can just write this as rho P0. And similarly, I can do the same thing and look at like this block here. So if I want to know what I want to ensure this box is stationary, what's going in should be the same as what's going out. What's going out will be just P1 times lambda delta will be equal to what's going in is P2 times mu delta again, I can cancel delta, and I will have P2 is equal to rho P1. And I can use the same argument again and again. Basically, I will have like Pn is equal to rho Pn minus 1, but this is equal to rho square Pn minus 2, and so on, will be equal to rho to the n P0. Now that's basically what we have now. And because these P are all probabilities, they should sum up to 1, so therefore, like, if I sum over Pn and equal to 0 to infinity, I should get like P0 rho to the n and equal to 0 to infinity and equal to P0 sum over rho to the n and equal to 0 to infinity. Here I will use a algebraic equality equation that this is equal to 1 minus 1 rho. Actually, basically in general we have something like n to some from 0 to let's say m rho to the n is just equal to rho n plus 1 minus 1 rho minus 1. So when m goes to infinity, I just have like 1 minus 1 over rho minus 1, so or like 1 over 1 minus rho. And therefore, like this, as we said, this will sum up to 1. So therefore, like P0 is just equal to 1 minus rho. So therefore, like Pn here, I substitute this back to this equation here. I can just have Pn is equal to 1 minus rho to the n. This is the stationary probability that you got. And with this stationary probability, we can kind of find the expected number of packets in the system, or expected number of customers in the system. This number of customers in the system will be just 1 minus rho to the n times n. This is expected number, or like average number of packets or customer in system is just equal to, so, and 0 to infinity, and is equal to 1 minus rho and rho to the n, and 0 to infinity. Against to sum over something like this, I can use a trick of taking derivative. Note that like we have this, let's say, when sum over infinity, I have basically this is equal to 1 over 1 minus rho. So now if I take a derivative of this thing with respect to rho on both left hand side and right hand side, for the left hand side I will have n rho to the n minus 1, right? So that's very similar to this guy here. And on the right hand side I will have like 1 minus 1 over 1 minus rho square. And then if I just multiply by rho here, then on both left and right hand side I will exactly have this here. So therefore this guy here is just 1 minus rho over 1 minus rho square is equal to rho 1 minus rho. So that's the average number of packet of, or like customers in the system is just rho over 1 minus rho. And then we can use the Little's theorem that the average delay, let's say t, is just equal to the average number of packets in the system over the arrival rate, right? So therefore it's just rho 1 minus rho over lambda 1 minus rho. And Okay, now let's compute the average wait time in Q. That let's denote as W. The average wait time will be simply the average delay minus the average service time, right? And as the departure wait is mu, therefore the average service time will be just 1 over mu. Therefore, average wait time W will be just T minus 1 over mu. And let's substitute T there. I have rho over 1 minus rho times lambda. And rho is equal to lambda over mu. Then I got some lambda cancel. And then that will be equal to 1 over mu minus lambda minus mu, 1 over mu. And that is basically just equal to rho over mu minus lambda. And then let's compute the average number of packets in the queue. And that will be just equal to lambda W by Little's theorem. And therefore it's equal to lambda rho mu minus lambda, and with some algebra we'll get rho squared over 1 minus rho.